Okay. I think we're on this. Shoot, I gotta check something else. Okay, we're chilling. Okay. Okay, so how we're gonna do this is we're gonna create a frequency array, and then we're going to iterate through all the values in all the characters in the string, and as we keep track of the frequency of each letter, we can make calculations based off of the current most common letter, and be able to determine whether we violate this replacement variable k. So as I iterate, I just need to keep track of which letter has the largest frequency and whether I have surpassed my replacement frequency allotment. So yeah. So here I can make free equals new int 26, then max free equals 0, and then so I'm keeping track of each frequency, the max frequency, and the output variable, which will be the length. Let's see. I actually think we need to do something like this. Keep left and right pointers. So while the right is less than s.length, we're going to keep track of each character. Cur minus a, and then we're going to increment the frequency, and then we're going to reset max frequency like this. And if the max frequency minus k plus 1, I think. Oh, wait, I totally misunderstood this problem. The sentiment's kind of the same, though. Max frequency. How do I do this? Wait. Right, left minus right. It's the other way. It's a right minus left. There we go. Yeah, okay, so space complexity is O of 1, because this is 26, so this is a constant. And then time complexity will be O of n, because this will only occur n times. We're doing a double pass, basically, rather than multiple iterations each pass. Okay, so this one you just do a rolling frequency check. So I'll take the length of this value and then I'll compare it to that exact same spot in the next string. And then if that doesn't work, then I'm going to keep on iterating like this until I hit something. And I'll hit this right here. But I'll do the same thing there. So if s2.length is greater than s1.length, this also will not work, so we're going to return false if that's the case. And then I'm going to make freq1 and then freq2 to store the frequency arrays of each. and then I'm going to iterate through S1's characters, and then calculate the frequencies. Is it lowercase? Yeah. And then if the string of, if the string of freq1 and freq2 equal each other, we're going to return true. And then we are going to iterate through the rest of the second string. So we're going to take s1.char at I, or no, sorry, s2.char at I minus a. We're going to decrement this, and then, sorry, I minus s1.length. We're going to decrement the, so if we move from here to here, we're basically going from 2 to 3, and then pruning the E off, so then it goes there. So that's what this line 20 does. And then this we can increment, and then we'll do the same thing here. So if they're equal, we'll return true. Otherwise, we'll return false here. Oops. There we go. So this is O of 1, O of n, O of, technically this is O of 1. And then O of n. So this is O of n plus m, where n is the length of S1, m is the length of S2. Oh, this is awful. Which one's this? Oh, this one's fine. Minimum window substring. I don't remember how to do this. I gotta check that. for fun. So I'm thinking we can do a 2-pointer with left and right where we track the characters that we run into, and then every time we fulfill all the letters, we calculate the length. And then we keep on sliding. So left I should probably explain all this again. So we have a left pointer and a right pointer, and then we want to track the length, the minimum length, and we want to track where that length starts. We also want to track the required characters that we are looking for here, and then we can iterate while right is less than length and store the current right character. I also think we need a frequency array. And for every letter in T, we want to take, are these all capital? Yeah. We want to increment it. And then if the current right character is what are we gonna do? If the current right character is a letter that we're looking for, so if it's greater than 0, what do we want to do? If it's greater than 0, we want to decrement required, and then we're gonna increment right. And then while required is 0, so when we've fulfilled this, we're going to close the window. So get the current left character. I think we can do something here too. So if min start is going to equal left, length is going to equal right minus left, and this is going to be if right minus left is less than length. Yeah. So we're going to take the current letter, and then we're going to Oops. Oops. Wait. So left. We're gonna take free curve left minus a minus, and then if no plus plus. So if that value is greater than 0, then we're going to increment required. Yeah. And then return length. I think that's it. Oh my gosh, bro. Is this not? Int cannot be converted. Oh, okay. S dot substring min start plus length, something like that. There we go. Oh. Now let's try it. Interesting. It does not consider bank. It only has to be like this. Wait. No, it needs to be like this. When did I? Oh, I never increment left, so that's why. There we go. Yeah, I was doing a lot wrong actually. This should happen after. I think both of these should happen after. Actually, no. Yeah, I think this should go down here. No. I'm doing something wrong. Oh, I have it wrong. There we go. Interesting. I'm gonna try this again. What's here? Yeah. Whoa, whoa. Whoa, whoa, whoa. No. Okay, something's wrong here. Looks like length is always infinite. Okay, there we go. I'm gonna try one more time. Oh my gosh, wait, did I do it again? What am I doing wrong? Huh. Oh. Okay, one more time. There we go. I think that's it. Because we have 3, 6, 7, 8. K is 3, so 8 minus 3 is 5, plus 1 is 6. Yeah. Okay. I think we need a deck as well. Is deck a linked list? Deck implementation geeks for geeks. Oh shoot, it's gonna give me a Python. Deck interface Java. How do you declare this? Array deck? Okay, wait, what is this? Interface, collection, queue, priority queue, deck, linked list, array deck. Okay, linked list it is. Array deck? I've never heard of that. So I'm going to go through each of the numbers. Oh, I'm not even explaining what I'm doing. Okay, so I'm creating the output array. Basically, we're going to create a sliding window literally just like this. And I'm going to track I'm going to add numbers, and then as I encounter numbers, I'm only going to add them if they're smaller than what I currently have. And then, so this would be 1 and then -1. And then if this position gets out of the window here, then I'm going to get rid of it, and then the next the next value. Wait, isn't this just a monotonic stack problem? It sounds like it. Honestly, let's try to do this with a stack. It might be easier for me. Stack, integer, stack, stack. I think there's an advantage to using a deck over a stack, though. Is less than nums, length, plus. So if stacked is empty, or nums stacked at peak is nums I is less than or equal to, or is it just less than? Yeah, I think less than or equal to. Stack dot push nums I. Okay. Alright, so then actually, no, we cannot do this with a stack. We have to use the deck. I gotta check this. So we have the output array, we need deck. Use our length, that plus. So if the deck is empty or deck.peak first, it's less than or equal to nums I. Oh no, it's the other way around. Yeah, something like that. Deck dot offer first I. And while let's do this right now. So deck dot offer last. I think you. Oh, this is actually tricky. While deck is not empty and deck dot peak first is less than nums dot length minus k plus 1. Deck dot pull first. 8 minus 1 minus k. Numbers down length. I think this is wrong, but we'll see what happens. I don't think I know this. I'm gonna look at the answer. Yeah, I've done it plenty of times. Yeah, so you do make a deck. So here, let's see. So if it's not empty and island is dead. So if the deck isn't empty and we're in the output range, why pull? Maybe this is later. Wow. Interesting. Okay, so let's see. Deck's empty, so we're gonna offer 0. That's not true. First block is not true. Second block is not true. Oh my gosh. I'm just gonna save this for later. All these linked list ones, I just like run through. Jeez. Okay. Okay, so to reverse a linked list, basically I can just show a visual demonstration. Actually, wait, sorry. 3, oops. 4, 5. Okay, so basically here, all we do is do this. We take this, detach, and then we flip this pointer, and then hold the pointer there. We detach, flip the pointer, and then store these in variables. That's literally all we're doing. We're just flipping the pointers. So we store previous, and while the head is not null, we store the next, which is head.next. So then head.next will equal the previous, and then previous will equal the head, and then head will equal next, and then we return previous. This will happen in O of n. Merge two sorted lists. Okay, so we have these two lists, and basically we're just going to iterate through them and then create a whole new list based off of which value is smaller. So if there's a smaller value, that will just be the next node in the list. So we're going to create a new list node called list. It's going to be empty. And while list 1 is not null and list 2 is not null, we are going to say list.next equals a new list node. Oh wait, sorry. Actually, before this, we're also going to carry a dummy node equals list. Something like that. Let me check this. Okay. So if list 1's value is less than list 2's value, then the next list is going to be a new list node with list 1's value. And then list 1 is going to equal list 1.next. We're going to iterate. Otherwise, list.next is going to equal list 2's value. And list 2 is going to equal list 2.next. And then we're going to iterate list.next, obviously. Now, if we have asymmetrical lists, if list 1 and list 2 aren't the same length, we have to individually do each one. Wait, actually? Oh yeah, this actually works. So if we don't finish list 1 or list 2, by the time we finish this block, one of the lists will have been exhausted. So that means either of the lists could still have some data in it. So we just do the same thing. 1.val, and then list 1 equals list 1.next, and then list equals list.next. And then we do that here too. Next list equals list.next. And then we return dummy.next to get the value. So this occurs in O of 1 time and O of n time and O of n space, because we have this new list that we're creating. I don't know if there's a constant space way to do it. I actually know. I don't think it would be possible. Okay, so this is just interleaving the interleaving the left end and the right end into one new one. So it would be 1, 4, 2, 3. That's 1, 5, 2, 4, 3. Yeah, just like that. So the way we're going to do this is we're going to split this list into half, basically. And then we're going to reverse the second half. And then we can reverse the second half. And then I believe we duplicate the first half and then place the second half into the duplicate values of the first half. And by doing that, we can make it that head is reversed like this, or what is it, reordered. So I'm going to make a new list node value called cur that tracks the head. So, actually wait. No, I'm not going to do that. I'm going to make a slow node equal head, and then a fast node also equal head. And while fast does not equal null and fastest next pointer does not equal null, I'm going to iterate slow once and iterate fast twice. So that will get us the halfway point. So slow is now at the halfway point. I'm going to set slow.next. I'm going to make it null to cut off, to separate the first half from the second half of the list. And before I cut it off, I will actually want to store the pointer. So there we go. So I'm holding the second half's head, and then I cut off the first half from the second half, and then I'm going to keep a pointer for the current head. Actually, no, I don't need to do that. So then I'm going to reverse. So next equals reverse dot next. The reverse head is going to equal prev. The prev is going to equal reverse, and then reverse is going to equal next. And that will be us reversing it. So now prev equals reverse. So head is there. I'm storing the head, and then I'm going to restore the reverse into prev. So while cur does not equal null and reverse does not equal null, I'm going to store temporary variables. So cur's pointer is going to now equal reverse, and then reverse's pointer is going to equal the temp1, cur's next value, and then cur will now equal that temp1 value, and then reverse will now equal its temp value. And that should be it. Next. Should be next here. There we go. So this happens in O of 1 time and, O of n time and O of 1 space, because we don't even manipulate. We don't have any extra space. Actually, do we? Technically, this is O of n space, right? Yeah. Actually, I'm very curious about that. This is also O of n space. What is the space? Time space. I guess it's all fun. Okay, so this involves having a fast node and a slow node. So I'm gonna create a new list node slow equals head, list node fast equals head, and then I'm going to iterate n times. Actually, I think we want to do n minus 1. It's n plus 1, actually. So we're going to have a fast node that's going to get ahead of the slow node, and then we're going to iterate until the fast node is null, and then that will land us, the slow node, at the node before the one we want to remove. So then we just remove that one. 1, 2, 3. Yeah. 1, 2, 3. 1, 2. Yep. Okay. So fast equals fast next. And then while fast does not equal null, slow is going to equal slow dot next, and fast is going to equal fast dot next. And then slow is going to equal slow dot next dot, or sorry, slow dot next is going to equal slow dot next dot next. And then we're going to return head. Then maybe it's this. Oh my gosh. Okay. Oh, I'm dumb. I actually do need a dummy. There we go. Oh, this one's fun. What was this time and space complexity? This is time complexity of n, space complexity of O of 1. Yeah. Okay. So there are actually two ways to do it. There's an easy way and there's a hard way. The easy way is to keep track of pointers, or keep track of the copy via a hash map. And then the hard way is to not use a hash map. So to use a hash map, I'll basically iterate through all these values and then store a copy of them in a hash map, and then I'll iterate through the hash map and then assign the old pointers to the new keys. Or sorry, the pointers like next and random to the values of the keys in the hash map, which will duplicate it. The hard way is to do it with that hash map, and I'll basically iterate through all of these values, or I'll take this entire list and then I'll duplicate it. So it'll be 7, 7, 13, 13, 11, 11, 10, 10, and then 1, 1, and then null. And then I will use the relative pointers and then use those to determine the copy pointers, and then I'll cut off the old values. So it's 7, 7, 13, 13, 11, 11, 10, 10, 1, 1. I'm going to cut off this 7, cut off this 13, cut off this 11, cut off this 10, and cut off this 1, and then I'll have a new linked, or I'll have a new list with the random pointers that wasn't the old list with those reference values. So I'll do the easy way first. Also, I don't know why they use node instead of list node here, but we make a hash map, and then we're going to iterate through the head. So we're going to put into the hash map the head, or the current value, I guess. And then this is bad code. Let me do another thing. Node cur equals head. So we always want to keep head original. So cur, and then new node with cur's val, and then cur will equal cur.next. And then cur is also going to equal head again, and while cur does not equal null, actually, can I do this in one pass? I might be able to. Map.get cur.random equals, oh wait, okay, yeah, I can't do it in one pass. Oh wait, no, I can't. I need all the values there. So cur equals head again, and while cur does not equal null, we're going to set the random pointers. So if cur.random does not equal null, map.get cur.random is going to equal map.get the random value. So we're getting the, if you notice, we're getting the copied value and assigning copied value, and then assigning the random pointer to the copied random value. And then cur is going to equal cur.next. I think I can also do map.get cur.next, or cur.next equals map.get cur.next. Yeah, so we can eliminate a pass here. And then we return map.get head. It's gonna fail. Oh my gosh. There we go. So that'll create the copy, and then this occurs in O of n time complexity, but also O of n space. This next one, we can get rid of the space complexity and make it constant. So here we'll have to get the cur again, and while cur does not equal null, we are going to store the next value, and then we're going to make a duplicate value and make that the next pointer, and then reassign the rest of the list, and then iterate to that portion of the list. So this is basically taking 7, and then we put something in between 7 and 13 right here, and it's another 7, and then we store 13. So then we set the new 7's pointer to 13, and then we iterate to 13. So we're going to do that for the rest of the list, which will be however many times that is. And then after that, cur is going to equal head again. And while cur does not equal null, so we're going to iterate through the list again, if the random pointer to cur does not equal null, we are going to set the duplicate's random pointer to the current's random pointer's next value. So if we have something like 7, 7, 13, 13, 13, 11, 11, 10, 10, 1, 1. So the second value is always going to be our duplicated value. So cur.random, this value's random pointer is null. So, okay, that's actually a bad example. Let's do 13. 13's random pointer is going to be 7. This 7 right here. So what we're going to do is, we know that 13's pointer is at 7. We're going to take 13's next pointer, which is the duplicate, and make it the random's next pointer. So it goes from 13 to 7 to the next value, and it stores it in this value. And that's how we duplicate it. And then cur is going to equal cur.next.next. And then we need to separate the values. So cur is going to equal head again. And while cur does not equal null, if cur, oh, wait. So cur.next, actually, head.next. Oh, wait, no, I know how to do this. Okay. So copy is going to equal head.next, and then the copy head is going to be equal to the same thing. And I'm going to do cur equals head, something like that. Yeah. So while cur does not equal null, cur.next is going to equal cur.next.next. So the original 7 is going to point to the original 13, and then 13 to 11. These are all original values. I'm resetting the original values. But then I'm going to say if copy.next does not equal null, I'm going to make copy.next equal copy.next.next. So I'm doing the same thing with the new created pointer. So cur is going to equal cur.next after that, and then copy is going to equal copy.next. And then I'm going to return copy head, which will give us our answer in O of 1 time complexity. I need a null handle. And there we go. Add two numbers. This is the dumbest problem ever, because we're doing addition in reverse. You literally just add two numbers, and then you hold on to a remainder variable to be able to handle double digit or sums that are greater than 1 digit. So can we make a new list too? Yeah, so I'll make a new list, and then I'll probably have a dummy variable too. And then while L1 does not equal null and L2 does not equal null, I'm going to store a remainder value, which is 0 for now. But list.next is going to equal a new list node with L1.val plus L2.val plus remainder. And then I'm going to take the remainder of that divided by 10. And then I'm going to make the remainder equal that same thing, L1 plus L2 plus remainder, except I'm going to divide it by 10. And then L1 or list is going to equal list.next, and then L1 is going to equal L1.next, and then L2 is going to equal L2.next. And yeah, that's it. And then if remainder does not equal 0, list.next is going to equal a new list node with the remainder value, and we return list. I actually think there's more to this. So L1 can be this block here. Oops. This block here. Oops. Oops. Wait, how do I do that? Okay, never mind. So this block right here can finish execution will finish before L1 or L2. L1 and L2, okay, basically when this block finishes, L1 or L2 have the potential of still being populated with values. So or we haven't like iterated through all the values. So we can do the same thing here, where list.next will equal a new list node, but except it's only L1's val. And then remainder equals the same thing. And then list will equal list.next, and L1 is going to equal L1.next. And then we do the same thing with L2, where list.next equals new list node, and then L2.val plus remainder mod 10, and the remainder is going to equal L1.val or L2.val plus the remainder divided by 10, and then the list is going to equal list.next, and then remainder is going to equal, or sorry, L2 is going to equal L2.next. Yep, so this will be it. Nice. Oh, dummy. There we go. So this is going to occur in O of n time and O of n space, because we're going to create, or sorry, technically O of m plus n, where n is list 1's length and m is list 2's length. Okay, so here, basically what we're going to do is we're going to have a slow and fast pointer, and then the fast pointer is going to go twice as fast as the slow pointer, and if the fast pointer ever hits null, we will have an acyclical list. If the fast pointer never reaches null, eventually the fast and slow pointer will will point to the same reference node, and if that occurs, then we know we have a cycle. So I'll make a slow node that is equal to head, and I will make a fast node that is equal to head, and while fast does not equal null and fast.next does not equal null, slow is going to be slow.next, fast is going to equal fast.next.next, and if slow equals fast, we're going to return true, otherwise we're going to return false. And this will happen in O of n. Oh, this is dumb. This is like the tortoise and hare algorithm. Basically, what you do is you'll have a slow and fast pointer, and you'll iterate until they equal each other. So you'll you'll iterate until they equal each other, and then you reset the slow pointers to the beginning, and then the fast pointer will go. Okay, I should rephrase. So let me restart the explanation. So you'll have a slow and fast pointer. The fast pointer will go twice as fast as the slow pointer. Same with the other one. You'll iterate until the fast pointer and the slow pointer equal the same number, and then when that happens, you reset the slow pointer to the beginning of the first number, sorry. And then you do it again with the fast pointer. The slow pointer iterates, and the fast pointer iterates twice as much. And then whenever they meet again, you will have your answer. And there's like a mathematical explanation to it. I think basically like, how do I explain it? So if these represented numbers, there will eventually be points in time so if these all represented numbers, right, and this represented the problem where there were some numbers and there was a cycle, here, when you iterate or when you have a slow and fast pointer that goes 1x and 2x, they will hit at the center of the cycle, and then when they meet up again, you'll get the origin of the cycle, like the node where it starts, basically. I could be totally wrong, but I think that's how it works. So we're gonna make a slow value, fast value. Oh no, this is another thing. It uses a do while. And then it like reverses it. I think it might be this. I actually don't think you go twice as fast the second time. Oh no, it's infinite. Okay. It does not that. Interesting. Why did I start at 1? Jeez. Maybe it's this. Yeah, it's definitely this. So I was right the first time. This you basically use a doubly linked list. Yeah, use a doubly linked list, and then you have you basically use a deck, but I'm used to representing it as a doubly linked list, and you have left and right pointers, and you store the least recently used in the left and then the most recently used in the right. And then as you interact with these values using gets and sets and puts and stuff like that, you either add a new value to the right side or you move something from the left to the right. So yeah. And then through that you're able to determine the minimum based off the key. Yeah. So I don't know how else I can describe this. Yeah, and then gets, obviously we're going to get the value and then return whatever's at the left pointer of the doubly linked list, and then we're just putting to the right of the linked lists. And then if we put a key that already exists, we're going to remove that from the left and then append it to the right. Or remove it anywhere in the doubly linked list. Yeah. Yeah, so firstly we're going to have to make a node class. So we're going to make a node class and we're going to have the value there. And we're also going to have it attached to nodes that have its previous and next value. And then we will have the constructor be the value that we want it to be. And then here, we're going to make a public node, or sorry, public int capacity, public node left, public node right, and then public, we're going to make a hash map too. Node, I think. Yeah. Because we want to be able to get the values as quickly as possible. So we're just using a hash map for that. So this dot left is going to equal a new node with 0. This dot right is going to equal a new node with 0 as well. And then we're going to make them point towards each other. So this dot left dot next is going to equal this dot right dot prev. And this dot right dot prev is going to equal this dot left dot next. So yeah, equals new hash map, and then this dot capacity equals capacity. Yes, I think that is mostly it. So yeah, these pointers are just our reference pointers to be able to access the least on the left, and then the most on the right, the most frequently used, and the least recently used. Let's start with get. So if the map or if this map does not contain the key, we're just going to return -1. Otherwise, what do we want to do? So if we get the key, oh, is that it? I doubt it's that simple. I think there's more to it. Get. Let's see, get. Oh yeah, there is more to it. We're gonna remove the node from the cache, and then we're going to insert the node from the cache. And then public void insert node. So to remove the node, we take the previous value from the node, and then we take the next value from the node, and then we say the previous value's next value is going to be next, and the next value's previous value is going to be the previous value. And then here, if we want to insert, we're going to make the previous value the most recently used value's previous value, and then the next value is going to be the pointer that we have. So then prev.next is going to equal node, and then next.prev is going to equal node, and then node.prev is going to equal prev, and then node.next is going to equal next. And this all happens in constant time. Yeah, I think that's it with get. I think that's it with get. Let's see, put. What is gonna be put? So if the map contains the current key. That's a different scenario that we have to handle. We have to take the node and then say this.map.get node, and we take the node's value and update it, and then we'll remove the node and then insert the node again. And then if we don't have it, we're going to check if we have hit capacity. Dot size is equal to this dot capacity. And if we have hit this capacity, then we are going to take the least recently used and we're going to remove it. Yeah. And then this .map.get or .put new node value, this .map.put key new node or node, and then insert node. And I think we are good. Capacity. Where? Oops. Huh? Next is null? This should not be possible. Oh. Where's LRU.val? This is interesting. That should never be null. Hmm. That's so weird. How is it? You should never get rid of the left. This means that right is the only value in the doubly linked list, which is impossible. It should be impossible. Because this means priv is null. But I'm assigning here. Oh, this dot left out next. It's this. I was doing it wrong. Okay, something's wrong. Why isn't it key here? It should be key. Hmm. Foot 3. This is where I'm tripping up. Do I need to store the key too? I might. I think I do. Yeah, there we go. That was the whole thing. Oh my gosh, that took forever. It took way too long. I got distracted. Dang. Whoops. Okay. Oh, I don't like this one. Okay. Oh, wait, no. This one's fine. Yeah, this one's fine. So you make a priority queue that stores list nodes. And then you make the comparison operator this. Oops. Jeez, my arm. Okay. Oh my gosh. This is awful. This problem is terrible. It's so difficult for no reason, too. So if the head equals null or k equals 1, then we can just return the head. Because if the group size is 1, then we don't reverse anything. But if it's anything but these two scenarios, then what we'll do is you store a group head. You store a group head, and so you'll store a group head. You'll iterate through k amounts of values, reverse them, and then add them back into the loop or into the list. And the only way I can describe it is by coding it. So we have group head here, which will equal, actually let's make list equals new, actually I think it was just dummy equals new list node. Group head is going to equal dummy. I think dummy.next equals list or equals head. And then and then we're gonna have a list node called, an integer called size. Make it 0. List node cur equals head, and then while cur does not equal null, we're going to track the size of the list node. Then, while k is greater than or equal to, or size is greater than or equal to k, we are going to perform operations. Yeah, I won't lie. I'm kind of lost after this. This is terrible. Size k. Hmm. Yeah, this is I'm looking at submission because this is really complicated. So complicated that I guarantee you if I look at this, I'll have comments for what to do here because that's how complicated it is. Yeah. So I got the first half right. So list node next node equals group head dot next. I got that right. Node to move equals next node dot next. 4 equals 1 minus okay. So next node dot next equals node to move dot next. So I need to detach the node to move. Okay. Then node to move dot next equals group head dot next. So I move the node to move, and then group group head dot next equals node to move. So we detach the node to move. We make that the head of the group, and then we reassign the group head, and then reassign the node to move. Like, I don't really know beyond memorization whether people can intuitively think of this. Found cycle. Pretty sure I have the same thing. Clearly I don't. Yeah, I don't. It's not very intuitive. I wonder what. Invert the tree. Okay. So we'll do DFS on the tree, and then we'll store the left and right iterations of the recursion and then just swap them. So if root is null, we're just going to return null. Otherwise, we're going to return DFS. Well, to be honest, we don't really need to handle this, do we? Return DFS root. So we're going to have public tree node DFS tree node root. We don't even need to do that. I'm done. So if root is null, then we're going to return null. Otherwise, we're going to store the left root.right, and then tree node right is going to be invert tree root.left, and then we were going to make root.left equals left, and then root.right equal right, and then return root. It's curves of O of n, space complexity of O of 1. Maximum depth of binary tree. So if basically we're going to iterate, and each level will increment a counter variable by 1, and then we'll return the max level that we encounter. So if root equals null, then we return 0. Otherwise, we're going to return 1 plus the max of max depth root.left, max depth root.right. And that will give us our answer in O of 1 time O of n time O of 1 space. Diameter of the binary tree, basically we count the max depth of the left and right nodes, or left and right leaves or subpaths, and then we do DFS and find and then add the depths together, basically. So it's like max depth, but with left and right trees. So I'm going to store a instance field here called diameter. And then if I'm going to run DFS on the root and then return this dot diameter. So if the root is equal to null, we're going to return 0. And then left is going to be equal to DFS root.left. Right is going to equal to DFS root.right. And then this dot diameter is going to equal math.max, this dot diameter, and left plus right. And then we're going to return 1 plus math.max left or right. Diameter is kind of like the wingspan of a tree, so we don't include the current node in the calculation. So to do this, we're going to basically do the same thing. We're going to calculate the depth of the left and the right path, and if the difference between those depths is greater than 1, then it is not balanced. So I can return DFS root, and if it equals to -1 or does not equal -1. So I'm going to create this DFS. If root equals null, then we return 0. And then we're going to calculate the left and the right. And if the left equals -1 or the right equals -1, or the absolute value of the left plus right, or left minus right, sorry, is greater than 1, we're going to return -1. Otherwise, we're going to return 1 plus the max of left or right, which will get us our answer. Same tree. So to do this, we just need to do DFS and make comparisons. So if P is null or Q is null, we're going to return if P equals Q. And then if the value of P does not equal the value of Q, we're going to return false. And then we're going to return is same tree, P dot left, Q dot left, and is same tree, P dot right, Q dot right. And we will get our answer. These are the comparisons. Subtree of another tree. So this is building on top of is same tree, but we want to make sure it's a subtree. So what we'll do is we'll iterate throughout all the values in the root, and then if we encounter a root that has the same root as the subroot, we will run the is same tree method, and if that returns true, then we're going to return true. So if the root equals, another thing is if the root equals null, null will always be a subroot of subroot. So we're going to return true. And then if the root is null and the subroot, if the subroot is null, a null subroot is always a null is always a subroot of a root, no matter if the root's null or not null. So we're going to return true. But if the subroot is null and the root is not null, or is null, then we're going to return false. And then we'll do if the root's value equals the subroot's value, and they're the same tree, we're going to return true. Otherwise, we're going to return is subtree for the left subtree and the same subroot, or is subtree for the right subroot and the current subroot. And then we will create is same tree. Boom. Done. Oh, I haven't been doing time complexity. All of this has just been DFS, so it's O of N. I think this is a Google question. Oh no, this isn't. Okay, so this we're just going to take the root's value and compare it to P and Q. If the root is less than both P and Q, we are going to go to the right of the subtree. And then if the root is greater than P and Q, then we're going to get to the right of the subtree. So yeah, and then we keep on doing that until none of those conditions are satisfied. And then we've hit our condition. So if root equals null, I don't even know what I do. I don't think I do anything. Yeah, so while root does not equal null, if root.val is less than p.val and root.val is less than q.val, if it's less than it, then we want to go to when we make it bigger, so we want to go to the right. So root equals root.right. Else, if root.val is greater than p.val and root.val is greater than q.val, we're doing the opposite. Root equals root.left. And then if those fail, then we're just going to return root. And then we'll return root here as well. Boom, done. This is log n because we get rid of half the tree when we iterate. Cool. Binary level. All right. What is it? Binary level tree. Okay. So here we're just going to do a BFS using a queue. So we're going to make a queue. And then the output list. If the root is null, we're just going to return the output. And then we're going to offer the queue the root. And then while the queue is not empty, we're going to get the size. And then we're going to initialize a level list. And then iterate the size. Grab the current tree or current value. If the current value's left tree or left leaf is not null, then we're going to take the queue and add that left leaf, and we're going to do the same thing with the right. And then we're going to take the level and add the curve's value, the current node's value. And then we're going to take the list and add the level. And then we'll return the level. There's the output. It is. Cool. Right side view. So this is the same thing, except we literally we take the last value in the BFS. So we're going to create a list of integers called output. And if the root is null, then we return the output. And then we're going to initialize a queue. And then offer the queue the root. And while the queue is not empty, we're going to take the queue's size. And that's it. And we're going to iterate throughout the size. We're going to get the current node. And if the current node's left leaf does not equal null, we're going to take that and offer it to the queue. If the current right leaf is not equal to null, we're going to offer that to the right. And then if I equals size minus 1, we're going to take the output and add the current node's value. And then we're going to turn the output. There we go. Oven again for both of those. Alright, this is actually more interesting. So we're gonna basically do DFS and then pass in. We're gonna do DFS and then keep a tracker of each subtree's parent node, and if that parent node violates the binary search order, then we're gonna return false. And then if it doesn't, then we're gonna return true. So we're gonna we're gonna return DFS root integer dot what, min value, and then integer dot max value. That might be flips, by the way. Tree node root, int min, int max. If root equals null, return 0. True, sorry. And then if root.val is less than or equal to less than or equal to min, or root.val is greater than or equal to max, then we're going to return false. Otherwise, we're going to return DFS root.left min root.val and DFS root.right root.val max. And I think this should do it. Yeah, there we go. I think these are longs then. Something like that. There we go. Okay, so this is actually pretty simple. So you just do an in-order traversal, store all those values in a list, and then get the kth value. So I'm going to make a list and then call in-order on it with the list, and then return list.get k-1. And that will be my answer. Root list integer list equal. If root equals null, return in order root.left list.add root.val in order root.right, and that should be it. Oh, list. There we go. This one's interesting too. So we can use the pre-order traversal to determine the roots of each respective subtree, and then using that root's value in the in-order traversal, we can recursively determine what's on the left and the right of it. So like we have 3 here, we know 3 is the root, and then we have 3 here. Everything left of the 3 is on the left side, and everything to the right of the 3 is on the right side. So then we pop that, boom, we do 9. 9, there's nothing to the left and the right of this because 3 we've already processed, right? So 9 is just an independent, it's just an array with one value. So that's finished, and then we move to here. So now 3 and 9 have been popped, and now you have 20. So we know 20 is the root, and we know 20 is here. So 15 we know will be on the right, left, and 7 will be on the right, and then you just keep on processing it recursively. So how we do that is we'll create an instance field called pre-order index, and then create a map that contains the in-order mappings, and then we'll initialize those values. So this dot pre-order index equals 0, this dot in order mapping equals new hash map, something like that. And then we take foreign dot user in order dot length. We iterate through all the in order values, and this dot in order mapping we'll put into it the value and the index. And then we are going to return build 0 in order dot length -1, and then pre-order, public tree node build int left, int right, int pre-order. So if left is greater than right, we're going to return null. And then we are going to make the root equal pre-order this dot pre-order index, and then increment it. So we're grabbing the root value, the relative root value, and then the left value will be build left this dot in order mapping dot get root dot val -1, and then pre-order, and then root dot right is going to equal build this dot in order mapping dot get root dot val +1 right pre-order, and then we return root, and that should be it. Oh, new tree node. There we go. Beautiful. And that occurs in O of n, where n is the length of the pre-order and the in order. But those will always be the same. N is the number of nodes, I guess. Maximum path sum. Okay, something important to note here is negatives. Negatives we'll always ignore. We're always ignoring negatives because null is 0. But we'll just do DFS, count the maximum path, and then return it at the end. So public int max, public solution, this dot max equals 0. So then we're going to DFS root return this dot max public int DFS tree node root. If root equals null, then we return 0. And then int left is going to equal math.max between 0 and DFS root dot left. Int right is going to equal the same thing. And then we're going to this dot max equals math.max root dot val, or this dot max, and then root dot val plus left plus right, and then we're going to return math.max left right. Okay, I did something wrong. Oh wait, no, it's root dot val plus this. Yeah. There we go. Alright, maybe I was mistaken. I was not. There we go. Okay. So we will what's the difference between pre and post order? Okay, yeah, we're gonna serialize in a pre-order traversal into a string builder. Um, yeah, just using the values. I think that's about it. So we'll make like a string builder, and then we'll use a like serialize helper, send the root and the string builder, and then return string builder dot toString, something like that. So if it's null, we're gonna append a pound sign, if I can find it. Yeah, there we go. And then we return. And then if it's not null, we're gonna do root.val, and then append a comma. We're gonna do the same up here too. And then we're going to recursively do this. Yep. And then for the deserialize helper, it gets a little more complicated. We do a BFS of the data split by this comma. So what we'll do is like, I think it's return deserialize helper data.split by the comma, and then this is wrapped into something that's like arrays.as list, and then q integer, or no, q string, new q string, and then we put this into the, yeah, something like that, and then public tree node deserialize helper q string q if string cur equals q dot pull, if cur equals the null, then return null. Otherwise, we're gonna get the root, the relative root, and make it equal to integer, or sorry, a new tree node with the string parsed as an integer, and then root.left is going to equal deserialize helper q, and then root.right is going to equal the same thing, and then we're going to return root, and I think we're good. If I can remember the semicolon. Maybe like this. Maybe we don't do this. Never mind. I wonder if I'm doing something wrong. Yeah, this looks right to me. I wonder what I'm doing wrong. I doubt it's very much. What the heck am I doing wrong? This looks identical. It's probably a lame typo. Oh. Of course, of course. Okay. Nice, nice, nice. Alright, I need to go to the bathroom. Oh, backtracking. I hate backtracking with a passion. I do not like backtracking. I've actually gotten a little better at it, but I'm just doing the prefix stuff. Okay, try. So you can use a node-based system to store current letters and a hash map of other letters. Actually, it'd probably be easier to store an array of tries, of more nodes, like try nodes. And you can use that to basically prefix all of this stuff. So, yeah. So I can make like something like this and call it the root. And say this.root equals new try node. And then make all of these, or make all these processes based off of the root. So I can take the try node class and say and then public try node letters cur. It doesn't even matter, to be honest. I could just do this. Public try node. I'm gonna make this 26. The size of 26 because I am only dealing with what, lowercase letters? Yeah. So if we want to insert, we say, okay, current node is going to be the root. And for every letter in this word, get the current character. And if the current character, or if the node, I think I can do index. So if the index is null, we're gonna make a new try node, and then make node equal node index, and then node.end equals true. And that is what I need to add. So public boolean I need something, an instance field that indicates that it's the end of the word, because we can have overlap. So if we want to search, then what do we do if we want to search? If we want to search, we grab the root, and then we iterate through the word, and we're going to grab the index, And if the index is null, then we return false. Otherwise, the node will equal the index. And then we're going to return node.end, because we can have a path that doesn't necessarily lead to a word that we have added. And then starts with is basically identical to search. So we're going to grab the node or the root, and for each letter in the prefix, we're going to calculate the index. And if the node index is null, then we're going to return false. And then node is going to equal node index. And then we're going to return true no matter what, because we're not looking for whether we added a word or not. We're looking for whether the path exists. Oh, shoot. I wonder if this works. I don't remember it working like this. Gotta check something, jeez. Okay. It does work. There you go. Starts with is O of n. Search is O of n. And then insert is O of n. Okay, so this is similar structure. Something like that. Okay. Adding words. We're adding a new try node every time we encounter a new letter. And then we're iterating to that try node. And then searching. So I'm going to iterate through each letter of the word. So if cur equals the wildcard, then we're going to iterate through each child in oh wait, no, this is not going to work. Whoops. So we're going to make a helper because we want to add a new parameter. I see why. Okay, actually, I'm going to redo this. So we're going to do everything the same, except we're going to make the children, instead of an array of trinodes, we're going to make a hash map. And I will kind of explain why later. So here we're making it a trinode instead. We're going to name this children. Okay. And then add word. So node equals this dot root. This is this. Oops. This is the same thing basically. We're going to iterate through each letter of the word. So if node.children.contains key cur. Oh, jeez. If it doesn't contain the key, node.children.put cur new trinode, something like that. Okay. And then node is going to equal node.children.get cur, and then node.end equals true. So for searching, we're going to return search helper, put in the word, add the roots, so we can pass in a trinode as a parameter. And then we're going to iterate. And we are going to grab the current word. And if cur equals the wildcard, we are going to iterate each child in node.children.values. Yeah. So we're going to run the search helper, or if search helper word child, then we return true. And then if we never return true, we are going to return false. And then if it's a traditional, if it's not a wildcard, then we're just going to do the normal processing. So we check if node.children.contains key cur, and if it doesn't, then we're going to return false. If it does, then node.children.get cur will be the next iteration, and then we're going to turn node.end. Okay, something seems to be wrong here. Oh, I think we just returned true. Oh, never mind. What am I doing wrong? Oh. Dot substring 1. Oh no. I plus 1? Yeah. There we go. There we go. Beautiful. Sweet. Alright, last one. Word search 2. I don't remember if I can do this. I also don't know why a try speeds this up. I just know that it does. So you can make like a try here. And then you can make class try, public try node root, public try root equals new try node, public add, public void add, string word, public void search string word, class try node is public boolean end, public try node children, public try node this dot children equals new try node 26. So we've made the try. And then I'm going to make the output list. And then for each string word in words, we're going to take try and add the word. Oh, I see now. And then for n equals 0, ist board length plus for j equals 0, jsp board length j plus plus. Return output. Actually, I think it's more complex. It's probably DFS. Yeah, DFS board try to root. Oh no! It's what I had before. But it's if board ij equals, or if try root if DFS ij row or board try dot root output dot add. Oh no, we're just gonna run this every time, I think. You can probably prove by saying like if try dot root dot. Would it be easier to do a hash map here? Let's just do this first. Let's do what I had, like this. And then what, output? Yeah, something like that. Public void DFS int row int call int board, or no, char? Yeah. Char board try no. Oh no, I should probably do this. Try list string output. If row is less than 0, call is less than 0, or row is greater than or equal to board out length, or call is greater than or equal to board row dot length. Return So if tried, I think, yeah, we can definitely do root here. If node dot next equals board row call minus a. If node index does not equal null. Well, if it equals null, we can return. Otherwise, we want to do node dot node equals node index, and then this should be Boolean, probably false. False. If DFS row +1 call board node output, or DFS row -1 call board node output, or DFS row call +1 board node output, or DFS row call -1 board node output. Return node.end. No, wait. That doesn't even matter. If node.end output.add I might have to halt this because I gotta go in 2 minutes, actually. Yeah, actually, okay. Actually, no. I'll write for 1 more minute. Because the try node needs to instead have string word. Word does not equal null. Output.add node.word, and then node.word equals null. Yeah, I think that's about it. And then adding is root, or try node. I'm gonna try to speed run this. Let's start root. Length plus in index try if node dot children index equals null, node dot children index equals new try node, node dot children index, node dot word equals word. Search try node is root for last word on index word dot child I word dot child I minus a. If node dot children index is null, return false. Node dot children index return node dot word equals null. Boolean. I don't even think we need search. They just write search for no reason. Node index dot children. This can be void. No way. Alright. I will solve this later. Have to go.